I want to spend some time talking about actual effects and what radiation actually is, how it kind of functions, and how it works. So when we talk about radiation, one of the things we can go back to is the idea of the electromagnetic spectrum. We know we have light, and we have different kinds or different classifications of light. We have radio waves, microwaves, things that are kind of around us. Then we get up into infrared, visible, ultraviolet, then X-rays and gamma rays. And we know that that increases in the frequency and a decrease in wavelength of the wave-like nature of light. We also have photons of light, where we have particular packets, of light, these sort of objects or particle-based depiction of light, where the energy is based on the frequency. And so one of the things is that these low frequency waves, so things like, radio waves, getting up into our cell phone waves, those have low frequencies. And as a result, the photons have low energy. So the individual particles of light have low energy. That's why we use those types of light to use for communication. You'll note on the examples here where we have things like, traditional AM/FM radio, TV signal, like over-the-air radio, cell phones, any sort of transmission, Wi-Fi signals that are in the microwave region. So the purpose is you're transmitting information, you're transmitting energy, but each packet of energy, each photon, isn't that high energy. So when it interacts with an individual molecule, like say in your body, it won't do a lot of damage. As we move up into higher frequencies, the photon energy becomes stronger and stronger, photon energy becomes higher and higher, and individual packets start to do damage. That's why you'll note there's this line right here that says ionizing, and above that we have really high energy photons, ultraviolet, X-rays, and then gamma rays. And these photons are such high energy that when they interact with a molecule, they're going to potentially cause damage to that molecule. They bring in just a lot of energy in one dose, right? In one packet that would hit right away. And so everything below that non-ionizing, everything that's all safe. Your cell phone isn't going to cause any sort. There is radiation there in the sense that radiation means energy traveling through space, but it's not strong enough to cause any effects. This ionizing versus non-ionizing is an important distinction between the types of radiation. It is a hard cutoff. But you'll know where you reach a certain frequency and everything above that is ionizing radiation and everything below that is non-ionizing radiation. And non-ionizing radiation can still hurt you, right? Like infrared, you can get burned by, just like a straight burn. If you put your hand next to an oven element, it will hurt. But that's heat effects. Those aren't specific light-based burns. Whereas like a sunburn comes from ultraviolet light. And so this idea of what is ionizing? What is this idea of ionizing versus non-ionizing? Well, we know ionizing means removing an electron, or forming an ion, right? So gaining or losing electrons. And so in the context of radiation, ionizing radiation is any light that has enough energy to remove an electron from a water molecule, right? Water tends to not want to lose electrons. But if you have a photon of light that has a really high amount of energy, it can bring all that energy in at one time and cause an electron to leave the water molecule. Okay, so this is generally high. It's in a bit into the UV where this can happen, and so that electron leaves the water molecule. That tends to not be something that would happen. The reduction, or the reduction potential, or that'd be oxidizing the water, right? It'd be losing the electron. The potential for that is quite high. So you have to put in a lot of energy, very non-spontaneous process that we're talking about here. But now you have this electron that is just free. Okay, it is now just not in the water molecule and it's just floating around. And so the reason why this ionizing radiation is bad is that these electrons that are liberated from the water molecules can just react with anything else. Electrons tend to want to be in molecules, and so what they will do is attach on to other molecules in the living thing. Generally biochemical compounds, your proteins, your fats, your sugars, your DNA, have particular structures for a reason, and they don't just have extra electrons. So when you have those extra electrons that just float around and attach onto things, they can cause devastating effects. And when you have DNA, that is the molecule that really runs and governs cells, right, the building blocks of a living thing, if you damage that DNA, the cell can functionally die. And so that is why ionizing radiation is really dangerous, because these electrons can go in and basically just break everything that's going on in the cell, causing it to die. And that's why ionizing radiation is really dangerous and why we care about that threshold, that cutoff of when photons become so energetic that they can remove electrons from water. So if we add into this the idea of all nuclear radiation, that was all energy or matter that came out from nuclear decay processes, or really any nuclear process. And we have three types that we care about, and we generally think about: alpha, beta, and gamma. Okay? So gamma radiation, that is photons. Those are the high energy photons that came out of our process. And gamma, and so everything we talked about, photons, still applies to gamma. And gamma photons are the highest energy possible. All gamma photons are ionizing. All X-rays are also ionizing, and gammas are even higher. And so even though gamma radiation and gamma decay wasn't really a type of process where you would predict a product or anything, one thing that's important to know is this gamma rays are emitted in every single nuclear decay process. There's so much energy involved that it all is emitted as gamma rays. So alpha emission and beta emission, and these are particles now. This is no longer pure energy. So alpha is a helium nucleus and a beta is an electron. So these are no longer photons. So it's not a question of what their frequency is. They are ionizing. We'll just say they are ionizing radiation. If an alpha particle or a beta particle hits water, it can remove an electron. Right? It makes sense. It's an electron, or it can also just make anions when you start to bring in extra electrons. We should note that X-rays are produced in electron capture. That was one of the signature of electron capture. And X-rays are dangerous. They are ionizing. But gamma rays also come out in electron capture, and they're worse. So you'd generally be more concerned about the gamma rays than the X-rays. Okay, so what do alpha and beta particles do when they come into your to a living thing? So again, the main molecule you're going to be concerned about in a cell is going to generally be the DNA, because that is the kind of building block, that's the control mechanism. And so when an alpha particle comes in, that is a nucleus. And these nuclei are flying, right? They are coming out with not only a high level of mass, but also just an extreme amount of speed. And so when this alpha particle, when this helium nucleus comes in and collides with another atom or another molecule, it just basically blows it apart like it would a cannonball. You are physically breaking moving atoms and breaking chemical bonds. Electrons are going to fly off as a result of it. This would just destroy any sort of molecule it hits. If that's an important molecule for the living thing or the cell, that can potentially kill it. And so this is extreme amounts of damage. It's not even that it chemically causes any effects. It just can physically break bonds by just moving atoms, because it itself is a nucleus with a huge amount of speed behind it. Electrons are not quite so damaging. In this case, they're not really doing physical effects. They're not moving nuclei out of chemical bonds. But what can happen is all of a sudden you have an extra electron on a molecule. And that can tend to lead to problems, right? You now have an ion, whereas you previously had a molecule that's not necessarily stable, can drive a lot of kind of bizarre chemical reactions that aren't meant to happen. Living things are generally built around really, really controlled chemical reactions, not just free for all, anything goes. So along these same lines, or along these ideas, we know all these different types of radiation are potentially hazardous and something we want to deal with. So then we want to think about, well, how can we protect ourselves from these radiations? So it ends up alpha particles, because they're so big and they just blow things apart, they're also the easiest to block. So if you want to shield yourself, a piece of paper can block an alpha particle. Just because the alpha particle is so big, it just will destroy molecules inside the paper, but it also gets stopped by that. If you have beta particles, they're now electrons. They're a bit smaller, they're moving faster. They would pass right through a paper. They would potentially, if you had like a beam of beta particles, some of them would cause damage in the paper, and then most of them would move through. If you had, say, like some lead, like a thin sheet of lead, now your beta particles would get stopped. Gamma radiation is going to be the most difficult to shield against. And they are produced in every single decay process. So if you have a piece of paper, some gamma rays affect the paper and damage it and then go right through. If you have, say, like a 0.5 centimeter of lead, pass right through that. if you have, with damaging along the way, if you have, say, 10 centimeters of lead, they would also cause damage there, but that's enough to block it. So that's about 4 inches of lead that you're now using to block gamma radiation. So in order to actually like protect something vulnerable behind it. So this idea of shielding, alpha's really dangerous, but also the easiest to shield. Gamma radiation is less kind of dangerous, it's more diffuse, but it still also causes, it's harder to block. And so if we think about radiation impingement on a person, if you have, say, an alpha particle that would collide with a person, okay, so in terms of how it would affect you, it's not going to get into your body. It's really easy to shield. So if it hit your skin, you would get a small burn on your skin because all those alpha particles get blocked by your skin. And getting blocked, what that means is that they basically have just affected molecules in the skin. So you could get what's called a radiation burn, which would be a skin burn from your skin from, say, a dose of alpha particles that was external. So it'd come in, hit your skin, affect your skin. If you were wearing a shirt, the shirt would block you, right? Anything like that would protect you. You could get damage to the molecules in the shirt. If you had beta particles, they would pass through you, they pass through a shirt, and they would then deposit inside of you and cause some issues throughout. Gamma radiation would just pass right through you, okay, for the most part. But importantly, it would also dose, you'd get radiation damage throughout the entire path length that gamma radiation went through your body. Nothing will block it, and it will dose all throughout. So this person has cells that are getting affected this entire length of the beam passing through their body. Also, generally, radiation doesn't necessarily hit you as a beam, or if it's a beam, it's more of, kind of a this-sized beam. So your entire body would get irradiated from that gamma radiation. So in terms of a person, alpha radiation from the outside, alpha radiation isn't that dangerous, right? Because if it's something that's going to come hit you, your clothes can block it, or pretty simple PPE can protect you. Gamma radiation, you need some serious protection. And so these ideas about penetration and kind of protection and stuff like that is one of the things that we can use radiation to our advantage. And so we use radiation, nuclear radiation, in a lot of different applications. So one of them, the most common one we'll talk about, smoke detectors. So the smoke detector in your house is run off of an americium, that's chemical symbol AM241. And so basically the idea of a smoke detector, on this little diagram, the left side here is the kind of normal behavior, that you have just air kind of flowing in a circuit. And what ends up happening is the americium source spits alpha particles into the air. Because they are alpha particles, they cause massive damage to the air. They ionize the air, right? They just blow apart electrons, make things are flying around. And what that then happens is you have charged particles in your air, so you complete the circuit. Okay, so circuit goes through and everything like that. If smoke fills your detector, that smoke now is blocking the alpha particles. So that prevents the flow of current, right? Because the air is no longer getting fully ionized and the current breaks, and then your smoke detector makes noise. That's why your smoke detector needs a battery, because that battery is then powering the current through the circuit that the americium is causing to be completed. Okay, and so that goes through right there. And so we can start to understand, why do we use alpha particles? Okay, we use alpha particles here because we need massive local damage, right? Air is enough to block alpha particles to some extent, right? The air is going to be the air right in the smoke detector is going to cause problems. We also don't want, say, like a heavy-duty gamma emitter, because that would then be spreading radiation throughout your house. So alpha particles cause huge amounts of damage right in the air that's close to it, allowing for that ionization to occur. And smoke is enough to then block it. The other thing is you want something that can cause a lot of damage and be blocked. Americium, so we could use any alpha particle. So then one of the questions when we're kind of designing things having to do with radiation usage, we can start to ask, well, why use americium? It's because its half-life is 432 years. Okay? And so that's not super short, right? Americium is not crazy radioactive. If you use something with a half-life of, say, months, Well, after like a year, your smoke detector's dead because there's no more americium left. So this is long enough that your americium won't burn out. So 430 years, after a couple of years, your americium is still cooking, right? It's still basically emitting the same amount, but it's also pretty short, right? This is still going to be very active in terms of radioactivity. You're still emitting plenty of alpha particles. You just aren't emitting, you're emitting, maybe a couple hundred a second as opposed to, billions a second.
Okay. No participation questions in this video. We are halfway through this set of videos. See if we find some more participation questions. See you there. Bye.